Hi, so what we're going to talk about today is solving closed forms for recurrence relations using the characteristic equation. Now, some of you in the discussion boards have already talked about how it's really inconvenient potentially to find the thousandth or the 10,000th or the 100,000th entry of a recursively defined sequence because you have to compute all of the values beforehand. And so the good news here is that we're not restricted to such techniques. Um, Given initial conditions and the recurrence, the only thing which determines what the value of a recurrence relation should be at that point should be the entry number, or n. So we should be able to express a sub n, the nth entry of a recursively defined sequence, solely as a function of n. And so in this video, we're just going to talk about a general form for the solutions to recursion relations and why they're solutions to recursive relations through the characteristic equation. So we're just going to take two steps back, and we're going to let a sub n be defined to be alpha a sub n minus 1 plus beta a sub n minus 2. And the characteristic equation is, as we can see, it's this thing here. That's what we call the characteristic equation. We take the recursive sequence r squared minus alpha r minus beta is equal to 0. So the first claim is that a root to this equation satisfies the relation. That if I take these coefficients and I can solve for what r's make that 0, that taking those to the nth power make the statement true. So let's go ahead and see why that's the case. Let's say we did have such an r, then what we're looking at is we are saying we're looking at r to the n as being a sub n, and then alpha to the n minus 1. If a sub n is r to the n, then a sub n minus 1 out to be r to the n minus 1. So backing up for just a second, this equation should hold if and only if we have that a sub n minus alpha a sub n minus 1 minus beta a sub n minus 2 is equal to 0, right? Then these things should be equivalent to each other. And so what I want to do then is evaluate a sub n and r to the n and see if I in fact do get 0. So we have here is a sub r sub n minus alpha r to the n minus 1. That's this here, or this here, I guess, minus beta r to the n minus 2. That's this here, right? Because we're assuming that a sub n has the form r to the n. And if I look at this, well, this really is r squared r to the n minus 2 minus alpha r to the n minus 2 minus beta r to the n minus 2, right? I can let everything be r to the n minus 2, and I can pop out some of the r's from these powers here to make that happen. And then I get to yank out all the r minus 2's, leaving behind r squared minus alpha r minus beta. But remember, where r came from was exactly as a solution to this equation, right? It's exactly one of the roots to that polynomial. So what we get is r to the n minus 2 times 0, which is of course 0. So if I look at this, any r that satisfies this equation here also makes this relation 0, which only occurs if the original relation is satisfied. So if I take the characteristic equation, any roots to that characteristic equation, those things to the nth power satisfy the recursion. All right. Claim number 2 is if that I have such a thing that satisfies the equation, I have an r to the n that satisfies the recurrence, then multiplying by a constant also satisfies the recurrence. And so let's check it out. Let's see if that's the case. So looking at this again, the claim then would be that, okay, C r to the n minus alpha C r to the n minus 1 plus beta C r to the n minus 2. Sorry, this shouldn't be a plus, this should be a minus. Then that thing, for the same reasoning we had over here, we want that to be 0. And then we notice that I can yank out a C from all of this. And we already know that that r to the n satisfies the recurrence relation, so this has to as well. So all of that has to be 0, and again this whole thing is 0. So what the second claim is that if any solution to the recurrence relation, I can multiply that solution by any constant, and that also gives me a solution to the recurrence relation. So not only can I take roots of my characteristic equation, I can also take multiples of my roots of the characteristic equation. All right. My next claim is that if I have two different solutions to my recurrence relation, then I can add up those two solutions, and that will also be a solution to my recurrence relation. So let's check that out. Let's say, so what it means to be a solution to the recurrence relation, let's go ahead and note that, is that f of n minus alpha f of n minus 1 minus beta f of n minus 2, that's got to be 0. And the same thing for the g's, right? G sub n minus 1 minus alpha g sub, or g of n minus alpha g of n minus 1 minus beta g of n minus 2. That has to be 0 as well. So if I take f plus g minus alpha f of n minus 1 plus g of n minus 1 minus beta f of n minus 2 plus g of n minus 2. Well, we should note some things here. First of all, I can distribute these negative alphas through and these negative betas through these sums, right? And once I do that, I should be able to group f's together and g's together. So this whole sum I can rewrite as f stuff, f of n minus alpha f of n minus 1 minus beta f of n minus 2. And then add the same things for the g. G of n minus alpha g of n minus 1 minus beta g of n minus 2. I can regroup this whole sum like that. And so from my observation here, that tells me this whole thing is 0 plus 0. So, to keep track of where we are, roots of the characteristic equation are solutions. Any multiple of roots of characteristic equations must also be solutions, and sums of multiples of roots of characteristic equations must now also be solutions. So there's only one last little thing to take care of. All right, our characteristic equation is quadratic. So generally speaking, it could have two roots, but not all the time, right? It's possible for a quadratic to only have one root. So that's what we're dealing with here. What if the characteristic equation can be factored, or the left-hand side of the characteristic equation could be factored into a single monomial squared? Then the claim is that that root and z to the n, in addition to z to the n, will be a root. So we should note, just looking at this, that a sub n minus 1 will be n minus 1 z to the n minus 1, and a sub n minus 2 will be n minus 2 z to the n minus 2. And so, in a similar spirit to what we've done before here, what I wanted to take is a sub n z to the n minus n minus 1 n minus 1 alpha z to the n minus 1 minus beta n minus 2 z to the n minus 2. Now I'm going to go ahead and jump ahead of some of this rewriting because it should be familiar. There is no a sub n there, sorry. We should get z squared n to the z n minus 2, and then followed by minus alpha z n z to the n minus 2 plus alpha z to the n minus 2 minus beta n z to the n minus 2 plus 2 beta z to the n minus 2. Alright, so far so good. Then I can group together the traditional pieces of this. We have a z to the n minus 2 here, a alpha z to the n minus 2 here, and a beta n z to the minus 2 here, and that gives me n z to the n minus 2 z squared minus alpha z minus beta. And then putting these two things together, I get alpha z plus 2 beta z to the n minus 2. Now the first thing we want to note, of course, is that by the same arguments as before, that's 0, so this whole first thing is 0. The second piece here is a little bit more subtle, but in order for z to be a solution to this equation, in order for this to factor cleanly, z itself has to be alpha over 2 in order for that to be sensible as a solution. And that means beta has to be negative alpha squared over 4. So if we put those facts in, we get alpha over 2 minus 2 alpha squared over 4 z to the n minus 2. And this whole thing, that whole thing turns out to be 0 when we simplify. So once again, this thing simplifies down to 0. So there's not much left to do. This characterizes all the possible solutions that a recurrence relation like this could have. So if I take my characteristic equation here, or my recurrence relation, and I look at the roots of the characteristic equation, there are two things that are possible. One is that you have two distinct roots, in which case these are the forms of your solution. The two different roots to the nth power and every possible linear combination, C and D, thereof. Or you only have one root, right? And what you get then is C times that root to the n, and D times n times that root to the n. So what's going to happen in the next couple of videos is we will show an example of solving one of these where you have distinct roots, one where you have a repeating root, and then show how you can use a little bit of Sage to help verify or check on your solutions. All right, thank you very much. Please let me know if you have any questions.